Hey Science 30s, and welcome to topic 1.3 of Unit C, Motors and Generators. Today I'm going to discuss sort of how magnetic and electrical fields come together to produce these two forms of technology. Motors, which take electrical energy and convert it into mechanical energy, movement energy, and how we can take mechanical energy and using magnetic fields, we can create electricity. Um, Before I get into today's discussion, you might want to take a watch of this video. This is going to be sort of a recap of all the major players that you might have remembered back from Science 9, folks that were involved in the early discoveries of electricity. You might want to just give that video a watch, just kind of get your head set, kind of put yourself into the, I guess, the electricity mindset, as it were, before I have my discussion today. But what I'd like to start with today is the discussion of two scientists. There were a lot of scientists in that video if you just watched it, but two scientists that play a particularly heavy role in today's topic are going to be Oersted and Faraday. Oersted was a Danish scientist who basically discovered, he was the first to discover, as I've been mentioning in both the videos already in this unit, that electrical fields or electrical current will create magnetic fields around them. So that was a huge, I guess, cataclysmic, I guess, not cataclysmic, but a revolutionary way of thinking about how electrical currents were not isolated, that they were inevitably linked to magnetism, so that electricity and magnetism were closely linked. I mean, the whole unit we're discussing is electromagnetic energy. So this was sort of the start of that understanding that both of these types of force, these types of energy, were basically were connected. One did not exist without the other. Now, after Oersted made his discovery, the next gentleman to come along was Faraday, and Michael Faraday. Pretty much a rock star. I mean, if you're thinking about your physicists out there, I mean, people think Einstein, but Faraday, possibly one of the greatest physicists of all time, certainly one of the most active experimenters in modern history. He did more experiments, was very innovative in his experimentation, and could really look at a problem and basically make an experiment to sort of kind of to solve the problem that he had. Faraday took what Oersted had discovered and said, well, wait a second, if electricity can create a magnetic field, then could a magnetic field create electricity? And he discovered that yes, it could. He discovered a concept known as electromagnetic induction. And he discovered two things that would have huge implications on the discovery of both motors and generators. In fact, Faraday created the first motor, which I'll get to in a couple seconds. He discovered that if you had a wire with current and if you had a wire with electrical current and you place it inside of a magnetic field, it would begin to move. And that discovery became the basis for the electrical motor, which I'll get to here later today. He also discovered that a moving wire inside of a magnetic field would actually create an electrical current. So if you just took a wire that had no electrical current in it and moved it into a magnetic field in a certain way, you would actually create electrical current in that conductive wire. So, and that became the basis for generators, which I guess I will get to later today. Now, he did build the first motor, like I said. The first motor was simply like a little, almost like a large petri dish that he placed liquid mercury in, and liquid mercury is a conductive metal, so it will conduct electricity. Inside that mercury, he placed a magnet with the North Pole facing up, and then he basically created an electrical current which was connected to a cell or a battery that was generating an electrical current running through that. And he dipped, the part of the current had a sort of a wire that was sort of fixed to almost like a little ring on the top, sort of connected with the metal, and it was kind of free to pivot. It could pivot around that point on the top. But this metal was sort of inside the liquid mercury. So when he turned on the power in that circuit, what he discovered was that little wire that was dipped inside that was connected to the top with that little pivot or that anchor point on the top. It was able to spin, like it basically spun around. It spun around the magnet in circular fashion. And that essentially was the first motor. And we've taken that concept and now we've refined it to basically make motors that power pretty much all the transportational devices that we use in our modern day. But Faraday was the guy who started that. If you want to see a little bit about Faraday, Faraday really some very, this guy is a rock star because everything we do nowadays with our use of electricity really boils back to him and his discoveries of electromagnetic induction. I mean, our electricity age is basically thanks to his discoveries that he pioneered. So give that a watch if you're interested in learning what Faraday did for physics and for electricity in general. All right, so again, his discovery of electromagnetic induction powered the way for the motor and for the generator, and that will be the remainder of today's discussion. What I've got here up on the board is a diagram, sort of a standard diagram that you would see of a motor. It's actually probably better than any of the diagrams of motors in your textbook. Unfortunately, the diagrams in your textbook aren't that great, but if you Google images of motors, this is one that tends to kind of crop up from time to time. So I'm going to walk you through this diagram, and again, it is on the next page in the notes. But a motor is basically a device that converts electrical energy into mechanical energy. So what we're going to do is we're going to basically put like a DC battery, a direct current battery or power source. We're going to run an electrical current through a circuit, and then we're going to basically run that. We're going to connect that onto what's called an armature, which is going to have a shaft attached to it. And that armature, if we can get that armature to spin, move, very much like what Faraday did with that little piece of metal that he did in his little mercury motor that he made back in the day, then we can create a rotational force that can basically power or be connected to wheels or any kind of a device that we want to actually move. So that's sort of the basis for a motor. Now I'm going to walk you through how the motor works. How do we actually get this armature to actually spin? Well, here's what we do. We've got an electrical source here in a battery or some kind of a power source that's going to generate an electrical current. And it's going to generate a current that's in one direction through this circuit. On either side of this armature, we've got what are called permanent magnets. There's two magnets, one's a north pole, one's a south pole. You remember that in our discussion about magnetic fields, the magnetic fields always run from north to south. So essentially what's happening right in between these two magnets, we're generating a magnetic field in between those two permanent magnets. And inside of that permanent magnet, we're going to run this little device, which is connected to our circuit. We're going to call that an electromagnet, because we understand that if I generate an electrical current, that's going to generate a magnetic field. So what we're doing is we're actually creating a magnet to go inside of the permanent magnet. This blue section here would be referred to as the electromagnet. It's only going to be a magnet if I'm running electricity through it. As soon as I stop running electricity through it, it has no magnetic properties whatsoever. The electrical current that flows into it is going to generate it and make it into a magnet, which will then react with the magnet that's there, that permanent magnet that's already in place. So how do we do this? Well, what's going to happen is this. This electrical current coming from the battery is going to enter and is going to make contact with a couple of metal brushes. Those brushes are going to get put against a device that's connected between the circuit and the electromagnet. That device is called a split ring commutator. And you'll notice that it's got two sides and it's split down the middle, and it basically has the ability to spin. It's actually attached to the armature. This armature that's a dotted line is attached to the split ring commutator, and the split ring commutator is connected to the electromagnet, which is going to continue the circuit. So like right now, this circuit, when it makes contact with this metal, is going to do this. I'm looking for my blue felt. Here's my blue felt. So right now, this circuit has made contact with this metal brush, this metal commutator, which means that right now my circuit is going to continue through my electromagnet in this way. It's going to run through this way, and then eventually it's going to come out this side. Well, we've created an electrical current through our electromagnet, so what's going to happen right now is this is going to generate a magnetic field. Now in this case, let's just say that this is going to generate a magnetic field that is going to have the north pole on this side of the electromagnet and the south poles on that side of the electromagnet. So we've got our permanent magnet that has a north and a south pole already. We've just generated a current through our electromagnet because of this split ring commutator, and it is generating a magnet inside of the other magnet that has a north and a south pole configuration, the same as the other one. Now that's a problem. We know something about magnets. A north to a north pole, are they going to be happy with one another if there's two north poles side by side? What did I say about poles and magnets? A north to a north pole, they're going to repel one another. A south to a south pole are going to repel one another. That's exactly what's going to happen. So here's what's going to happen. This is going to cause the electromagnet to actually flip. It's going to flip and do a half turn. It will do a half turn so that it orients itself in a south to north configuration. All right? So it's going to flip to make itself happy. This magnet inside is not going to be happy until its south pole is closer to the permanent magnet's north pole, and the electromagnetic north pole is closer to the permanent magnet south pole. But here's the problem. Here's not the problem, but this is the genius of this invention. What's going to happen now is it does a half turn. This is attached to it. The split ring commutator is attached to it, and it's going to flip and do a half turn with it. Well, as soon as this metal here breaks with that, there's a metal break, right? So when this side flips to this side, so imagine now this is, let me put it to you this way. Let me go back on my diagram for just 2 seconds. Okay. This is my north side when it started. And when we started, this side was number 1 and that side was number 2. Okay. So this was now basically, I'm going to go here. I'll just go 1 and 2 just to make, so my split ring commutator is 1, 2, it's north-south. Well, what happens now? If this side now becomes my south side and this side becomes my north side, that's not the only thing that's flipped half a turn. My split ring commutator is also flipped as well. This 2 now is over here, and the 1 is over there. Well, now that I've done that, this side, essentially, this side is no longer making contact with the current that's coming in from this side. The 1 is. So what's going to happen now is this. Because of the orientation change of the split ring commutator, what's going to happen in my electromagnet is this. My electromagnet is going to all of a sudden, the current in the electromagnet is going to flip direction. It's going to flip direction because my split ring commutator is oriented in the opposite direction now. Separate sides are now making contact with the original circuit. This circuit hasn't changed. All that's changed is the orientation of the split ring commutator, and that's going to cause my circuit in my electromagnet to change direction. Well, what does that mean about the polarity? If I change the direction of my electrical circuit in the electromagnet, guess what happens again? My polarity of the magnetic field will flip. So that's going to bring me back to a polarity of north and south, where the magnet inside of the permanent magnet isn't going to be happy anymore. So what's going to happen is it's going to need to flip another half turn again. So when it flips another half turn, we're going to be back to north and south, and my split ring commutator is going to go back to 1 and 2. Well, now that I'm at that point, again, I'm now making contact. This side of the commutator is now going to be making contact with the circuit again. So guess what happens again to the direction of my current? My current will now change direction again. It will go back to the way it was before the first turn. And because I flipped the current, I've alternated my current in there, again, my polarity will flip back to north and south, which is going to cause that electromagnet to flip a half turn once again. And I just repeat that over and over and over again. And what that's going to do, is it's going to basically take this electromagnet and it's going to start spinning. Because the electromagnet inside the magnet is now spinning, the armature that's attached to it is also going to spin. It's connected to the shaft, it's going to spin, and that's what's going to cause the wheels to go round and round. That's how a motor works. Kind of tough to explain on a board like this, so what I might recommend you do, watch this short video, little 1.5-minute video that's going to walk you through the animation of how an electrical motor works, very simple method about how it works and why it works. So take a watch of that video just to kind of maybe wrap your head around what a motor actually looks like. As well, as you can see here on the page that actually has the diagram that was just up on the board, if you read over pages 358 and 359 in the textbook, it also walks you through it as well, sort of step by step. But that's basically how a motor works. Another thing you can do, there's an analogy here on this page. I'm not a huge fan of it, but some people do like it. A commutator's role in the armature, in making the armature spin continuously, can be difficult to understand. Here's a couple of ways you can also look at it. Try imagining a steering wheel. So you're turning the steering wheel, right? I'm turning the steering wheel around and around and around. You put both hands on the wheel to turn, but can you keep turning without letting go? You eventually have to let go of the wheel, and then you basically have to keep grabbing the wheel. That's sort of what's happening here with that split ring commutator, is it's basically breaking the electrical circuit every half turn, which is causing an alternating current to go back and forth inside the electromagnet, which is continually changing the polarity, and that's what's causing that electromagnet inside the permanent magnet to spin round and round. All right, so there you go. If I only had a solid ring commutator, then I would only get a half turn. The permanent magnet would be happy inside of the electromagnet. It would be happy inside the permanent magnet, and you'd only get a half a turn of motion, and that would be it. So the split ring commutator is the linchpin in this operation. Without that split ring commutator, you can't continually make the electromagnet continually spin inside the permanent magnet. All right, that's motors. Generators. What's a generator? A generator is a motor in reverse. Basically, a generator is going to take mechanical energy and convert it into electrical energy, which is exactly the opposite of what a motor does. As an electromagnetic, a magnet spins inside of a permanent magnet, it can generate an electrical current, just as Faraday had predicted and proved in its experiments in the 1800s. However, the electrical current that's being produced is going to fluctuate, and it's always going to be highest. The current will always be highest when the two magnets are at right angles to each other. So if I've got my permanent magnet with my magnetic field going this way, if my electromagnet is at this position as it's flipping, right here is where it's going to produce most of the electrical current, then it's going to minimize its electrical current, maximize. Every time it goes parallel, it'll minimize the electrical current. So that is something that is a concern, because if you want steady electrical output from a generator, you need to somehow mitigate that increase and decrease in current to try to maximize the amount of output that you can get from a generator. So there are two ways that generators can generate electricity. You can either do what's called a DC generator or an AC generator. A DC generator, which is shown on the left, looks pretty much identical to an electrical motor, with one difference. There is no battery attached down here. There would be some kind of a voltmeter to read the electrical output. This is no longer an electrical input on this circuit. This would be the electrical output that we're now sending this electricity somewhere to be shipped to homes or to businesses. This would be sort of the output of the device rather than the input. The axis of rotation of the armature, the spinning of the armature, is going to create the electricity. So we need something that's going to actually spin the armature here to generate the electricity. We might have something like in a hydroelectric dam. You'd have water spinning over turbines. The turbines would then spin the armatures in the generators, and the generators then would have their electromagnets spinning inside of the permanent magnets, and that's what's going to generate electricity. So instead of generating the spin like motors do, the spinning comes before the electricity now, because we want to use this motion to generate the electricity that's inside of the generator, and that electricity then exits out through the circuit on the far end of that split ring commutator. So when you're looking at a difference between an AC generator and a motor, you have to look at the circuit to determine whether it's an input on that circuit or whether it's an output on that circuit, to determine whether it's a generator, a DC generator, or a motor. The second type of generator is alternating current, which what it does is it alternates the current back and forth, kind of like what we were seeing in the electromagnet in the motor. The circuit that was providing power to the motor from that battery would have been a DC current because it was always traveling in one direction. But then with the split ring commutator, the electromagnet would see the circuit change, the direction of the circuit would change, or the direction of the current would change, which would mean that that electromagnet had an alternating current in it. In this case, we're using an alternating current to generate electricity, and it's going to basically flip. It's going to alternate its current up to 60 times per second. So it happens very quickly. And because we're alternating the current, we do not require a split ring commutator anymore. Because it's AC current, there's no more split ring commutator. So how we notice the difference between an AC and a DC generator is this. An AC generator has two solid, non-split slip rings. So you'll notice that only the AC generator has two of these solid rings, no gaps in them, that are basically going to be the connection points for the electromagnet that's spinning because of the axis of the armature, the spinning of the rotation of the armature, and then that will then connect into a circuit that would then send its signal elsewhere to then basically be sent out. Now the question is, which do we use? Do we use AC or do we use DC power? Well, we use both. But it really boils down to transmission. The best way to transmit electricity over large distances is by using AC current. I'm going to get you to watch a video. A gentleman that you may have heard of before, a guy by the name of Tesla, was in a huge battle with a guy you would also probably know by the name of Thomas Edison. The two of them battled out for supremacy over what was going to be the dominant form of electricity in North America, whether it was going to be AC or DC. I'm going to get you to watch the video, and it'll show you some of the pitfalls of DC and why AC became the main way of power generation over long distances. Now, that said, we still do use DC a lot in our homes. Your iPhones, your computers, any small electronic devices are still being powered by DC power. But the power that comes into our neighborhoods before it enters our homes off of high voltage power lines, that's going to be AC generated power rather than DC. So we still use both, but right now the advantage for long-term electrical generation and transmission is still going to AC. Watch the video here about Tesla and Edison, and that will sort of hopefully wrap your head around the advantages or disadvantages of both. That's it. That's our conversation about motors and generators for today. Questions for homework are going to be questions 1, 2, and 3, and 6 and 7 on pages 364 and 365 of the textbook. Next time, we're going to start our first of two parts for section 1.4. We're going to get started on our discussion about electrical circuits. That'll be next time. Thanks for tuning in, and we'll see you soon.